G'day viewers, in this episode we are going to posit a solution to the element 115 mass density problem. Presently, discord exists between the value of element 115 mass density endorsed by Bob Lazar and the value of mass density estimated by standard nuclear physics theory, specifically by Emeritus Professor Burkhard Frick of Kassel University in Germany. The value endorsed by Lazar is 31.5 grams per centimetre cubed. However, the Frick value is 13.5 grams per centimetre cubed. These two positions are poles apart, and to make matters worse, Lazar's value simply does not fit in the way it should on the standard periodic table. So, what can we do about it? Well, one way is to take on faith that Bob Lazar did indeed utilise element 115. The second approach is to entertain the possibility that Bob Lazar thought he was utilising element 115, but was actually utilising an alternative element. Consider the following. Number one, Bob Lazar did not have any of the required apparatus in his laboratory in order to ascertain if he was using element 115 or something else. Number two, this means that he relied upon human testimony or documentation to conclude that he was using element 115. However, human testimony and documentation can be wrong, or worse, disinformation. Number three, whether or not Lazar was working with element 115 or something else does not actually matter with respect to reverse engineering the sports model spacecraft. Elemental knowledge was irrelevant in terms of what Lazar was employed to do, hence injecting element 115 disinformation into Lazar's situation was actually harmless to the project's objectives, but provides an important snippet of disinformation if the story of S4 was ever leaked. Number four, it would have been widely surmised by S4 information police that the synthesis of element 115 on Earth was inevitable and relatively imminent. Thus, spreading the story of element 115 serves to debunk Lazar's claims because it appears to be a fundamentally unstable element. So then, what do we think may have happened? Well, in this video presentation we demonstrate that element 247 ticks all the boxes, not element 115. We conjecture that Bob Lazar was given element 247 but was told that it was element 115. According to Lazar, both of these elements reside on an island of stability. The only way Lazar could have used element 115 is if its mass density was near the Frick value of 13.5 grams per centimetre cubed, not 31.5 grams per centimetre cubed as he claims. Okay, let's now take a look at the mass density of each element appearing on the standard periodic table. This is a graph of the mass density of each element appearing on the standard periodic table. It displays known mass densities from element 1 to element 97, with the exception of element 87, that is, francium. From element 98 onwards, all values of mass density are theoretical estimates, derived from standard nuclear physics theory. Notably, a significant contribution to the body of theoretical mass density estimates has been formulated by Emeritus Professor Burkhard Frick from Kassel University in Germany, as appears on screen. From this significant body of theoretical mass density estimates, one is of particular interest to us, that is, element 115. Upon inspection of the graph, we can see that the theoretical mass density estimates derived by Frick, that is, from element 104 to element 116 and element 156 to element 166, appear to follow the pattern of peaks and troughs we observe from element 1 to element 97. Recognising this attribute provides confidence in Frick's estimate of element 115 mass density. Having confidence in Frick's estimate is extremely important going forward, as we shall challenge certain aspects of the Lazar story by leveraging off Frick's element 115 mass density estimate of 13.5 grams per centimetre cubed. Let's now inspect alternative representations of mass density appearing on the standard periodic table. Appearing in the top left-hand quadrant of the frame is the standard periodic table with the mass density of each element depicted in cityscape format. Appearing in the bottom right-hand quadrant of the frame is the standard periodic table with the mass density of each element depicted in heat map format. In both of these representations, we can see that the mass density of element 115, according to standard nuclear physics theory, that is, 13.5 grams per centimetre cubed, fits like a silk glove. For example, the heights of the towers in the cityscape rise and fall in accordance with a recognisable pattern. Similarly, with respect to the heat map, elemental mass density decreases when we move left or right from the approximate centre of the row containing moscovium. Now, inspect the value of element 115 mass density taken from the Lazar website, that is 31.5 grams per centimetre cubed. With your mind's eye, raise the height of the moscovium tower by a factor of 2.3, that is, make the height of the tower 2.3 times higher than depicted. When we do this, we can instantly recognise that it does not fit the standard periodic table. In fact, it breaks it. Simply put, element 115 with a mass density of 31.5 grams per centimetre cubed does not belong on the standard periodic table. So then, how can we fix this mismatch issue? Well, we have a number of possibilities open to us, but before we explore what they are, we need to understand that the standard periodic table does not include all possible isotopes of every element. Just keep this in mind going forward. To resolve the element 115 mass density conflict, we can utilise four methods. The first method provides a linear mass density approximation for a broad spectrum of superheavy elements at a constant molar volume. This allows us to fill in the mass density blanks on the standard periodic table, which you will see on the next slide. Simply speaking, our first method utilises the Burkhardt-Frick mass density estimate for element 115 as a scaling baseline in order to approximate the mass density of many superheavy elements. In other words, we assume that the most recently synthesised isotope of element 115 possesses an exact mass density of 13.5 grams per centimetre cubed, which is the Burkhardt-Frick estimate. We then apply our nuclear isotope hypothesis in order to predict the existence of stable isotopes and their associated mass densities. As you can see on screen, our first method facilitates four scenarios. The first scenario estimates the mass density and atomic number of the primary fuel wedge if it resided on the second island of stability, which allegedly exists around element 247 according to Lazar. The second scenario estimates the mass density and atomic number of the primary fuel wedge appearing in the sports model reactor presented by Ken Wright. Please refer to episodes 59 and 67 for more information. In episode 67, the element 115 isotope 299 is utilised as the baseline reference. Hence, Burkhardt-Frick's mass density is tied to isotope 299 rather than isotope 290. This is why the second scenario may be associated with differing atomic number estimates. Moreover, it is important to note that the physical model displayed by Ken Wright was not constructed by Ken Wright. According to Ken Wright, it is owned by Lazar. We shall assume that it was fabricated by Lazar based upon his recollection of the model utilised at S4. The third scenario estimates the mass densities and atomic numbers associated with dimensional data supplied by Project Gravitor. We reverse engineer this information utilising the optimal 16-disk solution as a template, which revealed three potential configurations, as appears on screen. Unfortunately, due to a confidentiality agreement, we are unable to divulge the dimensional data shared by Project Gravitor. The fourth scenario estimates the atomic number associated with the element 115 mass density claim of 31.5 grams per centimetre cubed, as appears on the Lazar website. Let's now visualise our linear mass density approximation method with respect to the standard periodic table. As you can see, we are able to fill in the blanks via linear approximation. From this, two questions arise. That is, why do we need to do it and what value does it add? Well, the reason we need to do this is because no mathematical pattern fits the experimental data with a high degree of accuracy. If it were possible to fit a single equation to the experimentally validated mass densities of the elements, it would have been accomplished by the scientific community long ago. Thus, a linear approximation becomes an obvious step. The value that the linear approximation method adds is obvious once we declutter the graph, include 20% error bars and focus exclusively on the linear segments. Hence, we can see that our mass density estimate will not be correct all the time, but it will be correct more than just sometimes. Let's now move on to our second method to resolve the element 115 mass density conflict. The second method is applied to two scenarios. The first scenario involves the table appearing on screen, which is an extract from what is colloquially termed Joe Vanninetti's diary. Vanninetti claims that he worked indirectly with Bob Lazar whilst Lazar was stationed at S4. However, Vanninetti was stationed at Los Alamos National Laboratory. According to Vanninetti, he was a friend and colleague of Lazar and subsequently gained access to the information contained in the table, whilst he was employed by Lanell. At the very least, the value of mass density appearing in Vanninetti's table has been endorsed by Bob Lazar. We utilise the mass density and molar volume from Vanninetti's table to constrain our solution algorithm. In doing so, we conjecture that Vanninetti's mass density and molar volume data better suits element 165 rather than element 115. As we explained previously, the standard nuclear physics theory value of 13.5 grams per centimetre cubed is considerably lower than the value appearing in the table. This needs to be reconciled. Please take a moment to pause the video presentation and study our first method 2 scenario results. Okay, let's now move on to our second method 2 scenario. The second scenario involves Project Gravitor dimensional data, which has been endorsed by Bob Lazar. However, a confidentiality agreement between ourselves and Project Gravitor prohibits the release of this information. Having said this, we have developed a solution algorithm and can share the results with you. Of particular importance is the value of mass density, which can be calculated utilising the supplied dimensions. It is also important to understand that the supplied dimensional data is only approximate. An unknown margin of error exists with each dimension supplied. Nevertheless, we shall move forward on the condition that the dimensional data supplied by Project Gravitor and approved by Bob Lazar is precisely correct. Thus, we have determined that the dimensional data endorsed by Bob Lazar yields a mass density value of 35.7 grams per centimetre cubed. When we execute our method 2 solution algorithm, we find that the results returned better suit element 187 rather than element 115. Again, as we explained previously, the standard nuclear physics theory value of 13.5 grams per centimetre cubed is considerably lower than the value appearing on screen, that is 35.7 grams per centimetre cubed. This needs to be reconciled. Please take a moment to pause the video presentation and study our second method 2 scenario results. Okay, let's now move on to methods 3 and 4. The third method works backwards from mass density estimates in order to calculate the corresponding isotope numbers. When we execute this step, we see that the atomic radius associated with the Vanninetti and Gravitor mass densities is substantially different from the atomic radius specified by Vanninetti, that is 1.87 angstroms. In the case of the EGM estimate, the atomic radius corresponds to the Vanninetti value. Of particular importance are the neutron to proton ratios. In the case of both element 115 configurations appearing in the table, the ratios are exceedingly high and pose a significant issue to standard nuclear physics theory and implies instability. However, in the case of the EGM configuration, the neutron to proton ratio is almost unity and implies stability. The fourth method constrains the EGM configuration to the Vanninetti value of mass density. Please remember that this value has been endorsed by Bob Lazar. Thus, we calculate the corresponding number of neutrons. Hence, the neutron to proton ratio is almost unity, which implies stability. Moreover, once again, the associated atomic radius aligns favourably with Vanninetti's value. Let's now analyse what we have covered so far. We shall commence our analysis by considering method 2, 3 and 4 results. Upon inspection, it is immediately apparent that we may discard both configurations in the method 2 results table due to the comparatively large dissimilarity to the LAE-115 atomic radius published by Edward Halleritz in 2008. Of course, the LAE-115 atomic radius he references originates from Joe Vanninetti's diary. With respect to method 3, Once again, we may discard the configurations indicated due to the dissimilarity results. Thus, the remaining candidates are the EGM solutions contained in method 3 and 4 as emphasised by the red boxes. Okay, let's now analyse how these results impact method 1. If we review method 1 results in the context of method 3 and 4 results, it is instantly apparent that 5 of the 6 solutions presented may be discarded. Hence, the remaining method 1 candidate solution is element 247. Subsequently, by following the process pathway, we see that method 4 produces an ideal theoretical solution such that, number 1, the primary fuel wedge material is conjectured to be element 247, not element 115. Number 2, its mass density is 31.5 grams per centimetre cubed, not 13.5 grams per centimetre cubed, as required by the LAE 115 data table. Number 3, it contains 273 neutrons. This is 92 more neutrons than the element 115 stable isotope 296 conjectured by Storti. Moreover, it's 89 more neutrons than the element 115 stable isotope 299 conjectured by standard nuclear physics theory. Number 4, its atomic radius is 1.87 angstroms, as required by the LAE 115 data table. Number 5, its nuclear radius is 10.1 femtometers. Number 6, its neutron to proton ratio is 1.11, which implies stability. Okay, this all looks great, but there is one problem, and it's caused by Vannetti, not by EGM. Vannetti states 3 key requirements, that is, mass density, atomic radius and molar volume. As we have just shown, method 4 aligns with Vannetti's mass density and atomic radius, but when we analyse a little more deeply, we see that his molar volume value does not align with his atomic radius. In the top half of the frame, we can see that the LAE 115 table value of molar volume can only be achieved if the Vannetti version of element 115 with a mass density of 31.5 grams per centimetre cubed exists as isotope 424, that is, it contains 309 neutrons. In such a case, the neutron to proton ratio is 2.69, which is considered to be very high. In fact, such a high ratio implies instability. Moreover, we can also see that the LAE 115 table value of atomic radius is also dissatisfied. In the bottom half of the frame, we are presented with a solution which does work. Our results demonstrate that an element 247 solution produces an atomic radius satisfying the LAE 115 table value, as well as a neutron to proton ratio which implies stability, that is, 1.11. However, an element 247 solution requires a molar volume of 20.16 centimeters cubed per mole. This, of course, is in conflict with the LAE 115 table value. Therefore, we propose that the LAE 115 table value is incorrect. Okay, let's now summarise what we have learned. On our journey, we have learned the following lessons. Number 1. Bob Lazar endorses a mass density value for element 115 as being 31.5 grams per centimetre cubed, as displayed on boblazar.com. Number 2. Bob Lazar is not known to be directly associated with an element 115 molar volume of 13.45 cubic centimetres per mole, nor an element 115 atomic radius of 1.87 angstroms. Both of these metrics seem to have originated from Joe Vannetti. Number 3. Bob Lazar is not known to have actually determined personally, via physical measurement, that he was working with element 115, rather than some other element. That is, he was informed verbally or via documentation that he was working with element 115. It is possible that he was disinformed because knowledge of the specific element he was working with was not critical information for reverse engineering the sports model spacecraft. However, the mass density of what he was working with is too easily measured and verifiable to be disinformation. Number 4. The required number of neutrons for element 115 to possess a mass density of 31.5 grams per centimetre cubed implies nuclear instability. Number 5. The element 115 molar volume and atomic radius values reported by Joe Vannetti appear to be in conflict with each other in the sense that they imply nuclear instability. Moreover, they appear to be in conflict with standard nuclear physics approximations. Number 6. An element 115 mass density value of 31.5 grams per centimetre cubed appears to be physically impossible because it cannot be made to fit into the standard periodic table, which has been thoroughly tested since 1869 and is reliably correct. Number 7. The estimate for element 115 mass density derived by Emeritus Professor Burkhard Frick of Kassel University in Germany via standard nuclear physics theory, that is 13.5 grams per centimetre cubed, fits the standard periodic table extremely well. Number 8. We have considered various elemental possibilities as substitutes for element 115, and the only candidate we could find which ticks all the boxes is element 247. Number 9. We conjecture by forwardly executed mathematical derivation that isotope 520 of element 247 is stable, with a neutron to proton ratio of 1.11. It will possess a mass density of 31.5 grams per centimetre cubed, a molar volume of 20.16 cubic centimetres per mole, an atomic radius of 1.87 angstroms, and a nuclear radius of 10.1 femtometres. Number 10. Bob Lazar stated in a documentary that another island of stability exists somewhere around element 247. It is important to understand that we did not reverse engineer our element 247 solution based upon Lazar's island of stability assertion. Our element 247 solution has been forwardly derived via the electrogravity-magnetic construct.